So hello everyone, welcome to lecture 15 on finite element method. So I will, as always, start with a little introduction and overview of what we have done, and then we come to what we want to do today. So this was our map of the finite element method. And we started from a differential equation and we want to go to an approximate solution. And we talked about different types of approximations that are inherent to a finite element method. Then we talked about the nature of the strong form that is essentially a differential equation. And we also said, if you take that differential equation, that strong form, if you multiply it by a test function, integrate it over the domain, you come to a weak form. And that weak form would look like something like this. And now the weak form, as you can see, it's an integral. So not only it's an integral, but it also has 1 power less of the u. Let's say in this case, if u is the displacement, it has a weaker derivative. So it's why it's called also weak form. So for a very specific problem or for a simple problem here, you can see that we have an analytical solution, and then we looked into that specific problem, we derived the weak form of that one, and then we solve that weak form, that specific weak form, for a few different approximations, linear ones, quadratic ones, and cubic ones. And then, for instance, we saw that if it's a linear approximation, it could be a one-piece linear, it could be two-piece linear. If it is two-piece, it could be uniform or non-uniform. But then the important thing is that you should always remember that this is basically what you have. So that gray line that I have there, that analytical solution is non-existent. If you had that analytical solution, you wouldn't need finite element method in the first place. So basically, you should always think of these points as approximations. And also we discussed how these approximations, they basically relate to the derivative. And then it seems like they want to cancel the area between the analytical solution or the exact solution and the approximate solution. And then we also talked about this issue of, let's say, superconvergence, so that in one-dimensional finite element, you actually hit the exact solution. So we did that also for three-piece linear, we did it also for four-piece, and the observations remained similar. And if we do a quadratic function, then you actually hit the analytical solution. But also it means that if you have quadratic and above, so anything richer than quadratic, it always reduces to quadratic. So if your approximation space is large enough, you recover the analytical solution, the exact solution. So that was sort of what we did previously. And then we had this updated version of the same map that we started with. So again, the starting point is a differential equation. You calculate the weak form. But what we want to do now is to approximate, or to come to this approximate form via using shape functions. Okay, so it's a more systematic way of doing piecewise discretized form. Okay, so it's still a discretization technique, but it's just a different way of doing it, or different way of doing it via approximation. And then we started with this example that if I just give you a few points and I ask you to compute where that approximation would be, you can do it in your head usually. But if it is slightly more complicated, then you would do these sort of approximations using, let's say, polynomials and so on. But then we did this, let's say, exercise together, that if now you think of a cubic function like this, it's going to be a complicated case to do 4 equations, 4 unknowns. So the idea was to find something better for that, or a different technique for that. And this different technique is basically using the shape functions or hat functions or tent functions. And what they do is that they give you they give you unity at a specific point that you have defined that shape function for. and then they give you 0 everywhere. Okay, so basically this nice property, it tells you that if you have something, let's say a U, you can approximate that. Maybe I emphasize on this thing. So this is not, well, we write it as equality, but this is, maybe you would like to write it like this. Maybe let me just use the same color. It's an approximation of that. Okay, so you can approximate U to that. Again, we use it as equality, but in a sense that you know already this is an approximation, and from now on we work with that approximation. So these shape functions, they look like this. As we talked before, they have this property that, let's say, if you think of, I don't know, shape function n1, n1 must be 1 at node 1. So this is, let's say, node 1, this is node 2. Then n1, the blue line, is 1 at node 1, and it's 0 at node 2. And n2, the opposite. So n2 is 1 at node 1 and is 0 at, sorry, n2 is 1 at node 2 and 0 at node 1. Okay, it doesn't matter what are the coordinates of these points. As you can see, if you define these as such, they will basically adapt themselves such that they follow the property that we mentioned. Or if you think about these quadratic functions, for instance, is the same story. So this would be now your node 1. This would be node 2. This would be node 3. And you can see now at node 3, n3 is 1. At node 2, n2 is 1. At node 1, n1 is 1. So this is, again, think of it as node 1, 2, 3 with the coordinates A, B, C given here. Okay, so this is the idea basically. And then you can play with this. You can change these coordinates. You can do it in MATLAB by yourself. And the cubic functions also follow the same strategy. But now using that, we want to come back to this approximation exercise and see if we can calculate these functions. So let's say you have 2 points, or you know what U is at 2 specific coordinates, and then you want to calculate the approximation of U. So if you do it using exactly the technique that we just learned, so you just simply say U is sum of Ni, Ui, and then these Ui's are the values of U at those specific points or nodes. So if you do that, the first function would be U as a function of X is just X. Again, this is an approximation, obviously. And if you do this one, exactly the same thing, you just change basically the shape functions. Now you get, again, the approximation. And this is in principle the same thing as you have done before. It's basically just you have 2 lines and you pass, sorry, you have 2 points and you pass a line in between. So this is exactly that line. But it's a nice technique to do that. And you see this, let's say, the elegance of it if you think of a quadratic function. So now if you have 3 points and you need to pass that quadratic points, that quadratic function, it's exactly the same thing. So you write the same summation, and again, for you from a programming perspective, it's the same loop. So you just have a loop, like a for loop over the nodes, and the nodes go from 1 to number of points per element, something like that, or nodes per element. So it's just that loop, and it can automatically go to a linear, quadratic, or cubic function if you want to. So basically using the same technique, you can also write it for the cubic function. And as I mentioned, for your computer, this function is just good enough. So this is the answer. The fact that we like to order them and call, have the x cube first and so on, this is our own understanding of polynomial. Okay, for your computer, this is exactly that polynomial, and then basically it means the result of that loop in your code will do the job for you. Okay, so using this, then we come back to that problem that we had at the beginning. But now we want to use it, we want to solve this weak form using this approximation technique that we just learned. Okay, so we want to do it using this, and then, okay, I do it first for the linear one. So let's say you have a one-piece linear, you do the approximation, and basically if you just write the shape functions and you calculate it, you get the solution. So you can see what the, let's say, what the approximation is for you. Now, using this, you can also just, let's say, once you calculate the values or you solve that system, you can also write your line equation if you want to, because you know this is the equation of the line, and then now you know what is u2. So that's that. You can also do a two-piece linear approximation. So if you do a two-piece, it's a very similar thing like before, but now each piece, or let's say it's a linear approximation with 3 points. So two-piece means 3 points, but each piece is a line. So you can call it piecewise linear. Okay, so there is a first piece and there is a second piece, basically, but it's piecewise linear. And then you go through the same procedure, but now these integrals, you know, the one integral that you had, it's split into two integrals. Okay, but that function, it just is the sum of the same thing. Okay, so the function itself, it follows the same rule. You can imagine if it was, instead of two piece, it was three piece or more, it's the same thing. It's just, let's say if you had many pieces, then this shape function, which is 1 here, it's going to be 0 everywhere else at any other point anyway. Okay, so they would not have any influence for the points that are far from their, let's say, neighborhood. Okay, that shape function would only have influence on the nodes on its right and left side, on the immediate nodes on the right and left. Okay, not the points that are far. All right, so we can do that, and then basically using this and going through the mathematical steps, you calculate those values, those u2 and u3s, which u2 and u3, which are the unknowns. Okay. Now the key message was here, that in the previous approach, in the approach that we had, or I showed you at the beginning of this lecture, we write the line equations like this. Okay, so the unknowns are alpha, beta, alpha 1, beta 1, alpha 2, beta 2. Okay, it's the slope of the line is, for instance, the unknown. And then the procedure is the same. The intermediate procedure is the same. You just calculate the integral. You use the fact that your test function, your W, is arbitrary, and then you solve it. Okay, the procedure is the same. But if you do the first approach, the unknowns that you calculate are alphas and betas. So if you need your nodal values, which usually you need them because you design something based on those are the displacements, you still need to calculate the nodal values. In the current approach, on the other hand, we use this approximation. So now the unknowns here are the nodal values themselves. So they are not alpha and beta. They are u1, u2, and u3. Okay, so these are your immediate unknowns, which are indeed the nodal values. So once you solve the system, you get the nodal displacements and you're done. So the system is solved. Okay, so if you remember, I mentioned that we wanted to solve this problem using one-piece linear approximation. We did that in the previous lecture. Two-piece linear approximation, we did that also in the previous lecture. And now we want to do a one-piece quadratic approximation of that too. Before I jump to that, do you have any question? It was a summary of what we have done in like 6-7 lectures, I think, and that should bring you, let's say, to this point, and it should be now more straightforward for you to follow. Okay, so we want to do a one-piece quadratic approximation. So again, I try to draw that quadratic function here. So let's say I have a line. The line itself, it doesn't matter. I'm just drawing it so that we have a clear axis, let's say, to show the nodes. Okay, so this would be your x-axis usually. So let's say this is node 1, this is node 2, node 3, and then again, the coordinates of this, remember, this is a domain from 0 to 1. So the coordinates would be here would be 0, this would be 1, and then let's say the intermediate node is exactly in the middle, and we put it at 0.5. All right, now we want to draw the shape functions for this. Let's start with N1. So N1 is 1 at node 1 and 0 at node 2 and 0 at node 3. Let me see if I can draw something. Well, okay. So you want something like this, okay? So it's basically 1 at node 1, assuming that the coordinate here is just 1, this line is 1. It's 0 at node 2 and 0 at node 3. So this is N1. Does that make sense? All right, now we want to do N2. In order to do that, I try to just duplicate and maybe I can do the same thing here. So N2 is a function which is going to look like this. So you can see it's 1 at node 2, 0 at node 1, and 0 at node 3. Okay, so this would be N2. And then N3, I'm going to draw it in green. So N3 must be 0 at node 1 and 2, and it must be 1 at node 3. So it's going to look like this. N3 is this, N2 is this, and N1 is this. So what you need to do next is to write these functions. So I make these coordinates smaller to make space. So what is N1? Remember N1?
X minus 0.5 times x minus 1 over minus 5 minus 1.
Exactly. So it's x minus 0.5 because it's 0 at 0.5 times x minus 1 because it's 0 at 1, and then divided by the value of this expression at x equals 0, which would be 2, which would be 1 over 2. So I'm going to multiply this by 2 to save, let's say, vertical space because we have 3 of them. And so this would be your N1. And then again, if you like it so much, why don't I just write it like this? You can also, again, think of them like usual polynomials, if you like. Then we play the same game for N2. So N2 is going to be then similarly, again, 0 at 0. It's going to be 0 at 1. And then if you multiply it with the value of this expression at 0.5, you get this. I hope there is no mistake. By the way, please feel free to check my calculations and let me know if there is one. But it should be straightforward to see that. And then you have N3. So it's 2, again, x minus 0 now, x minus 0.5, and you have 2x squared minus x. All right, these are the 3 test functions. Sorry, not test functions, 10 functions. We will need their derivatives soon. So let me also calculate their derivatives. So n1 prime, the derivative of n1 with respect to x is 4x minus 3. N2 prime is minus 8x plus 4. You can calculate the derivative from this expanded form so that it's easier to see. And N3 prime is 4x minus 1. All right, so we have that. Now we come to our usual, let's say, standard procedure. Next, so you would say my test function W is N1 W1 plus N2 W2 plus N3 W3. And U is N1 U1 plus N2 U2 plus N3 U3. Now, again, because of the boundary condition here, remember, U at 0 is 0. So U1 is 0. 1 is node at 0, right? So U1 is 0. But also remember, we said if it's a Dirichlet type boundary condition, the test function is the test function is 0. So W1 is 0. Now we have this shorter version of each of them. The weak form, remember, the weak form is simply integral of W prime U prime dx from 0 to 1 is integral of W dx from 0 to 1. So all we need to do is to insert those into this. So W prime, so here you have W, you calculate W prime, and I'm going to insert it here. So if W is N2 W2 plus N3 W3, then W prime is N2 prime W2 plus N3 prime W3 times, and the same thing for U, N2 prime U2 plus N3 prime U3 dx. Now, here you could have used the values for n primes here. I mean, both here and here. You could have used them and then expand this further in terms of x and do the integration and so on. Okay, this is what we did previously. I want to intentionally not to do that. I want to keep it in this more compact form because I want to basically show you something different. There is a message we want to, or there is a message I want to convey, and you can see the message if I keep it in the compact form. If I put it in terms of x, then that message would be basically buried under powers of x. So let's just keep it in this compact form, or in this formal description. And the same for W2. So I'm going to put N2 W2 plus N3 W3. And then again, the same thing that I just mentioned previously at a different, let's say, at a different scale is also valid here. So these ends are nothing but the ends that we have there. So at this point, if you wanted to, all you have to do is to insert these functions in terms of x. You calculate that integral, then you would say that is valid for every w, which in this case means every W2 and W3. Okay, so if you did that, you would end up with two equations, two unknowns, and that's it. And from those two equations, you can calculate U2 and U3. Okay, you could have done that, but we don't want, I intentionally do not want to do that. Not yet. Does that make sense? Okay, so let's keep it in this form for now. Obviously, the answer is the same whether you do it that way or the way I'm going to show you, but then again, I think there is something to learn here. Let me just take this up here. So this is just our weak form, nothing complicated about it. So what we do instead is to expand these two, okay? So I'm going to multiply those two terms to each other. Okay, so we get this very long integral, basically, or very long argument in the integral. So you would get something which looks like n2 prime, n2 prime, w2, u2, plus n2 prime, n3 prime, w3, u2. So this is basically multiplying these two terms to the first one under second bracket. And then we do exactly the same thing. So now we are going to multiply these two. Plus n2 prime. What did I do? No, n3 prime. N3 prime, n2 prime, w3, u2, sorry, w2, u3, w2, u3, plus n3 prime, n3 prime, w3, u3. Okay, and that is equal to what we have on the right hand side. So for the sake of simplicity, I'm going to just keep the right hand side as it is, and I also make this smaller to save space. And then the right hand side is just, let's say, what we have here on the right hand side. I'm not going to write it for now. Let's think about the left hand side a little more and play with those two terms. Now, remember here we have two brackets, but also remember eventually the step that we want to do is that we want to use the fact that this thing is valid for any W2 and W3. Okay, so remember again, if you do the integral in terms of x, eventually you end up with something which would have W2 times something plus W3 times something equals 0, right? Remember we did that, and we said because W2 and W3 are arbitrary, then this is 0 and this is 0. So what I'm trying to do is to go through that step before we integrate. Previously, we integrated first, and then we did this game. now I want to play this game first and then integrate. Okay, that's the idea basically. I want to impose the arbitrariness of W in the integral version, not after we integrate. Previously, if you remember what we did last time, okay, somewhere here, remember we have this integral. This is from the last time. We integrate that, you get an equation which looks like this. Then you impose this arbitrariness and you get into this system, which tells you it's a two equations, two unknown, and you solve it. Now, that specific step, I want to go through it in the integral form. So I want to impose the arbitrariness of W before we integrate. That's the idea. Okay, so basically what I'm trying to say is that in the first term, or I want to end up with two terms, one of them is multiplied by W2, the other one is multiplied by W3. If you look at what you have up there, you would have like N2 prime, and then I would have N2 prime to the power 2, U2, plus N2 prime, N3 prime, U3, minus N2. Remember this minus N2 that I just wrote, it's actually from the right-hand side. That's why it comes with a minus, okay? So I'm taking W2 out, I take that minus. So you would have something which looks like this. Yeah, I make that first bracket larger to make it clear. Plus, now a similar game with the coefficients of W3, then you would have N3 prime, N2 prime, U2 plus N3 prime squared U3 minus N3. And then again, integral of that times dx. Now, all of this must be 0 for any W2 and W3. Does that make sense? Please feel free to interrupt me if you have any question. All right, now that we have this, maybe you already see what I'm doing here. And I'm going to just write this version of the equation instead of the previous one. So what we want to do is to play the same game here. You want to play the same game in a sense that I'm going to say, because this is equal to 0, and then because it holds for any W2, W3, it basically means that each of these integrals must be 0. Does that make sense? So again, you can play the same game as before. You can imagine first W2 is 1 and W3 is 0. And then in the second step, you can imagine W2 is 0 and W3 is 1. If you do that, then immediately they get out of the integral or they disappear. And then you end up with these two equations, two integral equations, which look like this: integral from 0 to 1 of that term, which was multiplied to W2 previously. I'm going to just duplicate and move it down instead of rewriting it. That term is 0. And then the other one. So this is your two equations, two unknowns. But now you have them in integral form. Does that make sense? So we didn't go through that step where we transform everything into X. We just stick to n's themselves. And then again, for your program, these n's, they are the output of a different function. So you can just call them later from the other functions anyway. All right, so let me just clean this up. Do you have any question?
Is there any physical meaning of W?
Not really. I mean, you can call it, this is the variation of displacement if you think of variational mechanics. So I don't know if some of you may be familiar with variational mechanics. This is basically that. Okay, so it's how much you can vary the system at a certain point. But for you, it's just an arbitrary coefficient. Okay. Yes. All right. Let's do these two integrals. But then again, before I even do that, I want to do one more game. Remember this simple problem. If you have something like, I don't know, AU plus BV plus C equals 0, maybe I actually write it as minus C so that you see even the connection faster. And then DU plus EV minus F equals 0. You can write this as A, B, T, E, so the coefficients matrix, times UV equals CF. Right? So you can do that. And that's exactly what we are going to do next to these two integrals. What we want to do is to, again, I can integrate it and do the same thing, but I want to do that before integrating them. I want to just keep them as they are. We can have these integrals n2 prime, n2 prime. Instead of n2 prime squared, I'm going to write it as n2 prime, n2 prime to make it even more clear to you. And then we will have n2 prime, n3 prime. And then you have n2 prime, n3 prime, surprisingly symmetric. And n3 prime, n3 prime, dx from 0 to 1. Now, this would be your, let's say, that matrix, that coefficient matrix that we just discussed about, that is multiplied to those variables unknowns. In this case, they are U2 and U3. Does it make sense? So this term, you see, you have integral of n2 prime squared times U2. This is basically this, plus the second integral times U3. Okay, that would be your first equation. On the right-hand side, obviously, we also write the right-hand side. So it's going to be integral from 0 to 1 of n2 dx here and n2, n3 dx here. Does that make sense? So remember, everything that we did, I just go back to the first step. Everything that we do is not different from what we had here. This is our weak form. we just insert those test functions, the shape functions. We expand that integral, we reorder the terms, we write those terms in terms of a matrix coefficient, and then we are here. Okay, so there is no, let's say, there is no assumptions, there is no additional magic step in between. It's just mathematical steps. Okay, so now what we want to do next is to calculate this thing together. So what is that first integral? Integral of n2 prime dx from 0 to 1. So integral from 0 to 1, n2 prime dx. What is that? So what is n2 prime? It's minus 8x plus 4. So n2 prime times n2 prime would be integral from 0 to 1, 64x squared minus 64x plus 16 dx. And if you integrate that, you get, I don't know, 64 times x cubed divided by 3 minus 32x squared plus 16x. And because it is from 0 to 1, well, at 0 is just 0. So all you have to do is to assume x equals 1 and evaluate this. Okay. So you want this from 0 to 1, which is basically its value at x equals 1. It would be 64 over 3 minus 32 plus 16. So that would be 16 over 3, I guess. Yes, so it's minus, so basically this is 16 or minus 16, that is 48 divided by 3. So 64 minus 48, that's 16. So that is 16 over 3. So that first integral is just 16 over 3. Now you can do the other integrals similarly. Integral of n2 prime, n3 prime dx from 0 to 1 is, now I'm talking about this term basically, right? n2 prime is minus 8x plus 4, n3 prime is 4x minus 1. I'm sure you can insert them, you can expand them, you can calculate them. It just happens that I know this by heart. So it's minus 8 over 3. Okay. Then you have the same integral, let's say down in this corner, you would have again integral of n2 prime, n3 prime dx. It's the same thing as you have on the other corner. So that is also minus 8 over 3. And then let's say n3 prime dx is 7 over 3. Now, what you need to do is to calculate these two integrals, 2. So integral of n2 dx from 0 to 1 is 2 over 3. Again, it's just you take n2 here and you integrate it, you insert value 0 to 1, you get n2 equals to over 3. That integral equals to over 3. and then integral of n3 dx from 0 to 1 is, it should be half of that. Okay. Yeah. No, sorry, not that. It's 1 over 6. Quarter of. Okay. So now you have all these values. What we want to do next is to insert them into this system and see what we get. So I'm going to just remove these values from the matrix. I just called it stiffness for some reason that maybe you can guess. So this is 16 over 3 minus 8 over 3 minus 8 over 3 and 16 over 3. And then in the second integral here, you would have 2 over 3, 1 over 6. Okay, now if you just look at the system, it's exactly the same thing as we had before. It's two equations, two unknowns, but we came to this in a more systematic manner. And if you just solve that, you would have u2 equals 3 over 8, and u3 is equal 1 over 2. Okay, and then again, at this point, you are done with the calculations. There is nothing else you need to do. So as I mentioned, usually the unknowns are just the nodal displacement, you have it done. But if you want to, if you are still asking yourself, what is u? you can construct that u at this stage. So you can say, well, u, remember it's n2 u2 plus n3 u3. Now you take n2 and n3, and you take u2 and u3. And if you do that, you would, let's say, n2 is minus 4x squared plus 4x times 3 over 8. u3 is 2x squared minus x times 1 over 2. And if you just calculate this, you would get your u, and maybe you can guess what that would be. So if you just expand that, you get your u, which is minus 1/2 x squared plus x. So our famous analytical solution that we had from the, let's say, beginning of this discussion, and it kept appearing here and there. So it's essentially the same thing, but in a more systematic manner. Okay. So again, this, remember, this was analytical solution. This was analytical solution. Okay. So again, not a huge surprise. We discussed that before. If you do a quadratic approximation, you expect it to hit or to cover the analytical solution. As I mentioned some lectures ago, we had done that here. So we did exactly this exercise, but last time that we did it, we used this coefficient. So they use the classical way of using polynomials, but eventually the solution was the same. But as I mentioned, this way was to show you or to teach you how the weak form works and how it's useful for us and how we can solve the solution for it. But it is not programmable. I mean, you cannot readily program what we did before. Whereas what we did today, to come to this, it's much more systematic. Okay, so we can program this, and I will show you how to program this. But before that, I give you a 10-minute break. So It's 2:25 now, 26, but let's continue at 2:35 in 10 minutes. Ready? All right, so we are back. Now, the next thing we want to do is again in line with what we have done before. We want to sort of make everything that we learned more systematic, more programmable. So remember what we had. This is our strong form. Okay, so we had this strong form, and then we said if you multiply it by a test function with these specific properties here, and you integrate it over the domain, that strong form, it ends up to become this weak form. Okay, so this is what I want to now start with. So the point of departure is, again, coming from a strong form to a weak form. And then I want to combine this discussion with the discussion that we just had previously, and then wrap up everything, let's say, under one umbrella. So let's say consider the generic strong form. I'm not going to say it is between 0 and 1 or anything. It's a generic strong form now. It's EA, let's say U prime, the derivative of that plus B, and we assume this holds for every X between alpha and beta. Okay, we don't say exactly if alpha and beta are like 0 and 1 in the previous example. This is any part of a domain, which could be 0, 1, or it could be a different size of domain. And then you would have boundary conditions too. So you may want to also add to it, this system is subject to boundary conditions at alpha and beta. So X equals alpha and beta. So this is your generic strong form. And I hope you do not complain, or you have not forgotten that if you go through the, let's say, through the weak form derivation process, so this is, let's call this weak form derivation process. And that simply means multiplying by test function and integrating. If you do that, then the corresponding weak form reads first of all, it's an integral now. It's an integral from alpha to beta. EA W prime U prime dx equals EA U prime at beta times W at beta minus EA U prime at alpha times W at alpha plus integral of B from alpha, sorry, integral, yes, integral of B, but integral of BW because you multiply it also by test. All right. So which again, maybe I hope you see the connection immediately, but if you don't, it is not, I mean, it's not something new. It's basically what we have here. So you can see the terms. Okay, so it's the same thing. We derived this before. So you can also derive it now based on alphabet. Okay, but now we want to sort of make some sense of it. We want to see what it means. Okay, so mathematically we know it's what it is, but let's say if we can sort of make sense of this. So the first thing, you can think of the last integral as, let's say, body forces over the domain, or this corresponds to body forces over the domain. Body forces over the domain. Okay, so that's your last term. And it just happens that we neglect this, okay? For now, just imagine it is 0. Now, does that make sense or not? You can sort of think about it in two different ways. First, you can think about it this way. Let's say you have a truss structure. I mean, this is 1D finite element. So our one-dimensional elements are representing truss elements, okay? So for a truss structure, it makes perfect sense to apply forces only at nodes, at endpoints, not through the truss, okay? So it's not a huge deal if you just assume this is 0. 99% of the time that you work with one-dimensional finite element, these are 0, okay? But let's say you have some sort of body weight, and then you cannot really neglect it in that sense. If you want to consider that, the thing that you can do is to just sort of lump it over the end points, okay? So instead of saying that, I don't know, something has a weight of 5 kilos throughout, you can just give, instead of saying that the weight is, I don't know, W, maybe you can have half of the weight at each of the end points, okay? So you can distribute this integral over the endpoints, okay? Either way, whether you want to neglect it or you want to just decompose it into nodal forces, either way, it's not a big deal. It's not a part of the problem that we want to deal with. It's a very minor point. So let's just, for simplicity, neglect that. Okay, I come to that maybe later in this course, and I tell you how to calculate that also for particular cases. But you can neglect it for now, and then again, if it is just a line, you can distribute the weight half and half, and it's okay. So that's the last term. Now, these two terms, in order to tell you what they are, I need to remind you of this example that we had in, let's say, ME 231 in mechanics and materials. Let's say you have a one-dimensional bar, okay? And then this bar is under some stress. Remember, we would say it's either tension or compression. And if it was tension, stress would be positive. If it is compression, stress is negative. Remember, we talked about that, right? And then at the time when we talked about this problem in the context of ME 231, we didn't talk about stress because we hadn't learned stress at the time yet. We called them internal force. So we said internal force is negative if it is under compression, internal force is positive if it is under tension. And many of you had that problem because it doesn't follow the direction of the forces usually as we do. Now we want to look at that again. So think about this and assume it's tension, okay? Let's just assume it is tension. If it is tension, that means you need two forces in these two directions. So I'm going to, maybe I can call this F, okay, let's call this F beta. Maybe this is point alpha, and maybe this is point beta. Okay, So this is F beta. Now, if F beta, if that force is 10, and this thing is under tension, that means on this side, you have minus F alpha. Does that make sense? So if you think about it again, think about F as being a number. Maybe that's easier. So think that's 10. So if this force is 10, and this force is also 10 in this direction, in our usual coordinate system, this would be a minus 10, right? So maybe, let me just put it as, why don't I put 10 here so that you can better understand what I mean? So I put just a number here, but in a usual coordinate system, this would be F beta, and then F alpha, it would be this one, meaning that F alpha is minus 10 and F beta is plus 10, right? So imagine these F's are just external forces at those points. Does that make sense? Very good. So, so F alpha, it's just, again, minus 10, and F beta here is plus 10. Now, what was that 10 anyway? So let's just use something more scientific than number 10. What is that 10? The thing that we just used there. It's that internal stress times area, right? Force is stress times area. So this was sigma A basically, and this was sigma A. And what is sigma? Sigma, by the way, is the same sigma everywhere, right? This is just that stress, that internal stress. And what is that stress? Sigma is E epsilon. And what is epsilon in a one-dimensional problem is U prime, is derivative of displacement. Okay. So basically what I'm trying to say here is to convince you that this thing altogether, if you just look at it, it's the force at the beta end, at the right end. It's the force at beta. And this whole thing, including its minus sign, it's F alpha. Okay, and the minus sign just comes from the fact that it is pointing into the opposite, well, let's say in the opposite direction to keep that member under, let's say, tension. It could be compression, and then they are both negative. Does that make sense? And here, F alpha and beta, these are external forces. At nodes, well, at nodes alpha and beta, which are your end nodes. So based on this, let's say, explanation, then I'm going to remove this and write it like that. So this, the right-hand side would be W at beta, so it's a test function at that point, times the force, the external force at that point, or the right end. And then you would have W alpha times F alpha. Please pay attention, now it comes with a plus sign, because we just mentioned how the minus sign disappears. Okay. And if, remembering that you would neglect this term, I'm going to also omit that completely from the picture. Maybe I put also this thing on the corner to remember that. Here. Okay, so it turns out that the weak form that we just derived, it's nothing but, I'm going to, so the next thing I'm going to do is to take EA out, okay, to make it even look better. So if you take EA out, then you would have some integral from alpha to beta EA, and then the right-hand side. So this is your weak form now. Okay, and let me see if I can draw a square around it, or rectangle. So this is pretty important, and we will be using this quite frequently from now on for the next examples. Okay, so let me see if this works. All right, so if you need to remember one thing from the beginning of the course until now, is this weak form. Now, what we want to do is to play exactly the same game that we played before. We want to approximate this now. Remember, that's what we always did. We derive the weak form, we do the approximation. Now, we want to approximate this using one-piece linear and one-piece quadratic test function. Well, the domain, the functions, approximations. So let's do one-piece linear and one-piece quadratic. Okay, so as I mentioned, this is our weak form. I keep the weak form there. What we want to do is to do two approximations. So we have learned how to approximate things. So this is the task now. Approximate using one-piece linear one-piece quadratic. I just want to write something here also. Let's say two-piece linear maybe. But rather, I want to ask you why I am not asking you to do a two-piece linear. I'm not asking you to do a two-piece linear, but I put that question mark there to remember that we talk about it, okay? There is a good reason for not doing that. So let's do a one-piece linear approximation now. And this approximation, we want to do it using our new technique, obviously. So using shape functions, not what we did before. So if you have a one-piece linear approximation, and I'm going to draw the same domain, let's say like we did before, think about it this way, that you have a domain maybe from 0 to 1, but not necessarily. So it would be from alpha to beta now. And this would be node 1, and this would be node 2. We'll write the nodes on the side. So this is node 1, this is node 2. And the coordinates are alpha to beta. Okay, so this is coordinate alpha, this is coordinate beta. Now again, if you want to think of the n1, this would be n1. It's 1, let's say at node 1, and this would be N2. It's 1 at node 2 and 0 at node 1. Okay, so these are your shape functions. Now we want to write these shape functions too. What are their functions in terms of, let's say, x coordinates? So N1 is, remember, it's the same thing that we did before. It should be 0 at node 2 with coordinate beta, and it should be 1 at coordinate alpha, so we just do this. Now, this is the generic form of that function in terms of any alpha and beta. And then N2 is x minus alpha divided by beta minus alpha. Now, maybe you can imagine that this alpha and beta are arbitrary coordinates, but if you think about a truss member, what is more important for you is the length of that. So the length of that member is L. Okay, so let's say the length here, if you think of it as a truss member, the length is L, which means it's beta minus alpha. So beta minus alpha is L. In other words, you can write these shape functions like 1 over L times beta minus x. And the second one would be 1 over L times x minus alpha. So these are basically your test functions in terms of beta and alpha. And then L, the length of the domain, is already in there, which you will see why in a minute. Now, the test function W can be written as N1W1 plus N2W2. Okay, so that would be the approximation using these shape functions. And U is N1U1 plus N2U2. Now we do the same thing like we did the last time. We don't want to insert these as x coordinates and integrate. We want to keep them in this compact form in terms of n's to see if we can see something more interesting from them. So the weak form would be EA, integral from alpha to beta. Now W prime U prime, you just put it there. W prime is N1 prime W1 plus N2 prime W2. That's W prime. U prime is N1 prime U1 plus N2 prime U2. Dx, that's, let's say, the left-hand side. And your right-hand side is just W at 2, F2, force at 2, plus W1, force at 1. Okay? It's that simple. Now, what we do next is, as we did previously, we just expand these terms in the integral. So it's EA, integral from alpha to beta. And while I'm expanding it, I also do that second step, which I take W's out. So it would be W1 times a term which would look like N1 prime, N1 prime, U1 plus N1 prime, N2 prime, U2 plus W2 N1 prime, N2 prime, U1 plus N2 prime, N2 prime, U2 dx. And this thing is equal W2 F2 plus W1 F1 for every W1 and W2. Okay, so what you want to do next is the same thing as we did before. Now we have this system which is basically two equations, two unknowns. Okay, so you play the same game. You assume two scenarios. Let's say W1 is 1, W2 is 0, and then W2 is 1, W1 is 0. So from the first system, these two terms, from the first system, these two terms will vanish. So this would be your equation. From the second system, these two terms will vanish. So this would be your equation. This thing is equal this thing. Okay, so I'm going to write this thing as two equations, two unknowns. Then you would have EA, integral from alpha to beta, EA, integral from alpha to beta. In the first system, that integral would be the first bracket, which I'm going to just duplicate and put here. In the second system, would be this one, dx equals, now in the first system you get f1, in the second system you get f2. Remember the w's, I just canceled them out from left and right after going through this step, right? So the w's, the coefficients w1, w2, they are completely absent now, which we expect them to go away, right? I mean, they always go away at the end or at some point. All right, so you have now this system. It's two equations, two unknowns. And what I'm going to do next is to just write it down. As we spoke before, we want to distribute this in a matrix form, right? We can do that as we said. So if you do that, you would have these terms. You would have EA integral alpha to beta n1 prime n1 prime dx, EA integral alpha to beta n1 prime n2 prime dx, EA integral from alpha to beta n2 prime n1 prime dx, and EA alpha to beta n2 prime n2 prime dx. Okay, so this is your coefficient matrix. That times the unknowns, which are u1 and u2 here. You may call them u alpha and u beta, by the way, but these are u at node 1, u at node 2, which again could be alpha and beta. That would be equal f1 and f2. All right, so you see, it's like a mystery that it is kind of unveiling itself step by step, and soon you will see what this thing is. Okay, so we have this. Now let's do these integrals. Let's calculate the integrals as we did before. So integral of n1 prime from alpha to beta is what? Any guess? So n1 prime is minus 1 over L. So minus 1 over L times 1 over L, that is 1 over L squared. So it's basically integral from alpha to beta of 1 over L squared dx, which would give you 1 over L squared, x from alpha to beta, which is beta minus alpha divided by L squared. But remember, the length L was actually beta minus alpha. So this is 1 over L. Okay, so each of these integral terms, it just happens that they are 1 over L. And maybe they remind you of something. So each of these are just EA over L with a sign difference. So this is EA over L. This is minus EA over L. You can maybe track the minus from the difference of the sign here. And then this would be EA over L with a minus again, and then EA over L. Okay, so it ends up basically being just EA over L times 1 minus 1 minus 1, 1. Now maybe you can call it U1, U2. And that would be equal F1, F2. Okay. And obviously, I think at this point you recognize this guy, but to make it even more clear to you, and I'm going to remove this test function and stuff. You see, they basically did their job, so we don't use them anymore. If you define K or effective K, some sort of stiffness of the member as EA over L, this system is K minus K minus K and K times U1, U2 equals F1, F2. Okay. Now I think you see the big picture basically. So from the strong form, from a strong form which was this, we calculate the weak form, we do the approximation, and we end up with this system. The system, the very system that we used at our first lecture, I think, right? So this is lecture 1, I think. And yeah, here. You recognize that here. But I started from this. So I started the lecture from this because I wanted to teach you the assembly, and I wanted to let you do the, let's say, the projects and work with the truss structure. So that is more like a structural view to finite element method. So for the finite element method, you can have a structural view, and this is basically what we did. You can sort of look at this system without knowing or without really explaining what is the mathematical connection to this stiffness matrix. So we started from that structural perspective because I think it is more exciting for, let's say, for students. And we learned the assembly and everything. And now after 15 lectures, basically, we come to the same system, but we now also understand the mathematical description. Okay. Now, it turns out that if you want to go to a two-dimensional finite element method, you need the mathematical description. Okay, so for one-dimensional finite element method, because you can always think of these elements as springs, the connection, so you don't need really to connect a differential equation to a spring for one-dimensional case. For a two-dimensional finite element, there is no spring. all you have is a differential equation. So when we want to do the next part of the lecture, when we go to two-dimensional FEM, then we need to do that. Okay, that's one thing. So let's come to the exercise that we just had together, or I just mentioned a few minutes ago. So this is what we wanted to do. And now we have the answer to one-piece linear. So it turns out if you do one-piece linear, you can write your system. I will just call this thing stiffness matrix. And I will write that stiffness matrix as integral, I write that stiffness matrix as EA, integral from alpha to beta, n1 prime, n1 prime dx, integral from alpha to beta, n1 prime and 2 prime dx, integral from alpha to beta n2 prime and 1 prime dx, and integral from alpha to beta n2 prime and 2 prime dx. Now, also from this picture, you can clearly see that this thing is symmetric. Remember, we had also this discussion on the symmetry of the problem. So this one is n1 prime, n2 prime. This one is n2 prime, n1 prime. But the integral is the same, so it's also a symmetric matrix. So basically, if you do this one-piece linear solution, you can say your system is K times U, vector U, is equal vector F. Now, U would be here U1, U2, or U alpha, U beta, and vector F would be F1, F2. And basically, this is your K. Okay, so this is the first part of this exercise that we had together. Now, remember, I had this question. So why am I not asking you to do a two-piece linear? Because that's a very stupid question to ask. I mean, if you have two-piece, you can do 2 times one piece and assemble them together. You have learned how to assemble them. Okay, so basically, if you have n-piece linear, it's just assembling n different pieces one by one. Okay, so this makes no longer any sense to ask this type of question. Okay? So it just follows from the assembly procedure. So okay, maybe I answer that here. So and it follows from assembly. So you don't have to worry about that. But we want to also do the quadratic one. Okay, so if you remove that thing, and also remember this stiffness that I wrote here, maybe I can just write it in our form. It's basically K equals EA over EA over L. 1 minus 1 minus 1, 1. All right, so you have that. Now we want to play the same game for the quadratic one. So if it is quadratic, maybe you have a good feeling of how we should extend this to a quadratic case. And this is actually one of your homeworks. So I will just sort of tell you this, so the answer. But you can connect the dots. It's not difficult. So you would have now a vector which has 3 force forces, because these are three external forces at your points 1, 2, 3, or at nodes 1, 2, 3. And then your stiffness matrix would be a similar story, but you can imagine slightly larger than this. So let me just zoom in. If you look at this stiffness matrix, maybe you can recognize the structure. Here at first row, first column, you have n1 prime, n1 prime. First row, second column, you have n1 prime, n2 prime. Then you have n2 prime, n1 prime, n2. So if it was a quadratic function, again, it's not something that you have to accept my word or memorize it. It's something that if you do the calculations, the derivations, you see it. So, but that thing holds. So I'm going to just write it here. It's going to be then integral from alpha to beta, n1 prime, n3 prime dx here. Then here it would be integral from alpha to beta, n2 prime, n3 prime dx. Okay, and now just for the fun of it, I'm going to duplicate this instead of rewriting it. And then we had here, you see, you have these 2 primes. I just remove them and make them 3 primes. Okay, that's all you have to do. And then once you are having this form, all you need to do is to do these integrations. And these integrations are very simple. These are just polynomial integrations. So that's that. So it would be a 3 by 3 matrix. And just to have your nodes complete, if you do that, that 3 by 3 matrix would look like EA over L times, just push this down a little. EA over L times, let me take a 3 out, EA divided by 3L, 7 minus 8, 1 minus 8, 16, minus 8, 1 minus 8, and 7. Okay, so it would be this. And these numbers, by the way, just remember this 7 over 3 and minus 8 over 3. If you remember what we did before the break, you know, when we calculated this quadratic approximation, you had seen it before. So you have calculated this integral already once, for not for this full domain, because in that example n1 was Dirichlet node, so it went out. But these are this 16. You see this one 16 minus 8 minus 8 7. This is basically what we have here. It's this part of it, because we remove the first row and column because it's a Dirichlet type boundary condition. It's just multiplied by 0, and it's like your static condensation that you used to do, right? So that goes out. Okay, so that's it. We are exactly at 3:20, and this is exactly also what I wanted to get at. The last thing, or it's not the last thing, the next thing that we need to do in our map is to calculate these integrals. So you see, we have this now in this very nice systematic form. The only problem is that these integrals are not yet calculated. So the next thing we want to do is to learn how to calculate these integrals numerically. Okay, so that's essentially our next step. So we started from strong form, we go to weak form, discretized form. We now did the approximation. This is the next thing we want to do. We have that approximate form. That approximate form looks like a very nice matrix. but we still need to calculate it or integrate it. And that integration, we do numerical integration, which we'll learn in the next lecture on Friday. All right, thank you very much. Have a good afternoon. Bye-bye.